You know when you're setting up a new profile, you finally think of the absolute perfect handle, and literally the millisecond you finish typing it in, that little green checkmark appears? Well, how in the world does a platform with billions of active users instantly verify if that exact username is up for grabs? And how do they do it without completely crashing their servers in the process? I mean, it kind of feels like magic, right? But the reality is just pure engineering brilliance.
Welcome to This Explainer. Today, we're diving into a brilliant piece of system architecture that keeps our favorite massive-scale apps running smoothly. We're going to decode the invisible machinery operating behind every single keystroke, specifically looking at how Instagram handles username availability at an unprecedented global scale.
I mean, we've all seen this screen. You type in a name, something like _traveler_99, and instantly you get that available confirmation. It seems incredibly simple on the surface, but the back-end magic required to actually pull this off, checking your new idea against billions of existing accounts instantly for millions of people signing up globally all at the exact same time, is absolutely fascinating. If they tried to do this the traditional way, the whole system would basically grind to a halt.
So here is our roadmap for today. Number 1, the billion user problem. Number 2, enter the Bloom filter. 3, how the check works. 4, Redis cache versus Redis Bloom. 5, more than just Bloom. And finally, number 6, the massive impact.
All right, part 1, the billion user problem.
Let's talk about the hidden villain of our story here, the astronomical computational cost of something engineers call database hammering. To really grasp this, we have to respect the sheer challenge of scale. Instagram is handling billions of usernames. Imagine a massive, heavy, traditional database sitting on a server somewhere. Every single time someone types a letter, C, then O, a traditional setup would have to go ask that massive database, hey, does this exist? What about this? What about this? Checking that primary database for every single keystroke is unbelievably slow. And doing it globally, with thousands of signups happening every single second, that risks completely overwhelming or hammering the main database until it literally fails. They desperately needed a shield.
Which brings us to section 2, enter the Bloom filter.
So to solve this massive bottleneck, engineers don't just throw more raw memory at the problem or buy way bigger servers. Instead, they introduce a remarkably efficient tool called RedisBloom. It relies on a Bloom filter, which is a type of probabilistic data structure. Think of it like a highly efficient VIP bouncer at a massive club. Now, this bouncer doesn't actually know every single person on the gigantic guest list. That would take way too much brainpower. But they have perfectly memorized exactly who is definitely not allowed inside. When a Bloom filter looks at data, it very quickly tells the system one of two things. Either this item definitely does not exist, or this item may exist. It never gives a definite yes, but its definite no is 100% trustworthy.
And to save all that space, the filter doesn't actually save full-text names like _traveler99. Instead, it runs the name through an algorithm and just stores tiny hash fingerprints. It maps the data to a simple bit array of zeros and ones. Because of this little bit of mathematical magic, it delivers 0 false negatives. That means if it says a username is available, it is absolutely right. Now, it does allow for possible but very low false positives. So it might occasionally say a name might be taken when it actually isn't. But honestly, in the world of system design, that is a perfectly acceptable trade-off because it handles the vast majority of checks instantly.
Moving on to section 3, how the check works.
Okay, let's walk through the exact step-by-step flow when a user actually types a new username into the app. It's this brilliant multi-layered defense. Step 1, the user types a new username. Step 2, RedisBloom intercepts it first to perform that lightning-fast, quick existence check. Now, if the Bloom filter returns a 1, meaning the name may exist due to those false positives we talked about, the system doesn't panic. It just moves to step 3 and checks a traditional Redis cache. And only if there is a miss in that cache, meaning the cache doesn't know either, do we finally reach step 4 and hit the heavy, slow user database for final verification. So the filter basically acts as the ultimate frontline shield.
But here is where the real power kicks in. If RedisBloom returns a 0, meaning definitely not present, Instagram immediately knows the name is free, because remember, there are 0 false negatives. It completely bypasses the cache, completely bypasses that heavy database, and returns that beautiful green available text to the user instantly. Just like that, millions of heavy database queries are simply eliminated.
All right, part 4, Redis cache versus RedisBloom.
Now you might be thinking, well, why don't we just use standard caching for all of this? Why even bother with this complex probabilistic filter? Well, the differences are stark. A traditional Redis cache is designed to store and retrieve actual data, like full keys and values. Because of that, its accuracy is 100%, but its memory usage is incredibly high. It's fantastic for storing active user sessions. RedisBloom, on the flip side, is purpose-built strictly for checking existence. It only stores those tiny hash fingerprints. So yes, its accuracy is probabilistic, but its memory usage is astoundingly low. It is built purely for existence checks at a massive scale.
Let's put this into perspective with some real-world numbers, because the contrast is wild at scale. To store 1 billion usernames, a standard Redis cache would need over 50 gigabytes of expensive RAM. RedisBloom achieves the exact same frontline goal using just 1 to 2 gigabytes. That is an absolute game changer for infrastructure costs, all while actually speeding up the user experience.
Which leads us to Section 5, more than just Bloom. But the engineering ingenuity actually doesn't stop there. The RedisBloom toolkit is packed with other specialized structures for different data challenges. For instance, standard Bloom filters can't really delete data easily. But if a user deletes their Instagram account, the system can swap in a 𝗪𝗂 filter, which is similar but fully supports deletion, to easily free up that username again. Then you've got the 𝗏𝗵𝗲𝗰𝗸 sketch, used for the approximate counting of massive rapid events. This is how platforms instantly track top hashtag counts or search trends without melting down. And finally, the top case structure is specifically designed to dynamically find the most frequent items in real time, like top trending reels or top locations. It's just this whole suite of probabilistic superpowers.
And finally, Section 6, the massive impact.
Let's zoom out for a second. Why does this architectural choice actually matter so much to the broader web ecosystem? Well, Instagram secures 4 massive wins here. They get microsecond existence checks for an incredibly snappy UI. They dodge millions of unnecessary database hits, which protects their core infrastructure. They massively reduce their memory footprint, turning 50 gigs of required RAM into just a tiny fraction of that. And most importantly, the whole thing scales flawlessly to billions of users. User number 2 billion has the exact same frictionless experience as user number 10.
And the crazy thing is, this isn't just some isolated trick used only for social media signups. These exact same probabilistic data structures run the modern internet. They power huge e-commerce platforms checking inventory. They're heavily used in security and fraud detection to instantly cross-reference malicious IP addresses. Massive search engine crawlers use them to know if they've already visited a specific web page. And real-time data analytics companies absolutely rely on them worldwide to process streams of endless data.
To wrap this all up, this whole process perfectly captures a core philosophy in modern system design. Sudhir Verma, the creator of our source material, really hit the nail on the head here when he said, sometimes the biggest performance improvements come from avoiding database queries altogether. It's not always about just building a faster database. Sometimes it's just about being smart enough to not ask the database a question in the first place. So next time you are setting up an account and you instantly score that perfect username, take a second to appreciate the hyper-efficient mathematical machinery running behind the scenes, and ask yourself, as we build the next generation of massive apps, what other hidden bottlenecks could we bypass entirely using a little bit of probabilistic magic? Thanks for joining me on this explainer. Keep asking great questions, and I'll catch you on the next one.